Congratulations, you have made it to the final chapter of data. The remaining two chapters are summaries and conclusions. Let me start right out by saying that this is not going to be about global warming. Instead, I want to focus on more linear, less complicated, and I believe more immediate concerns. The primary intent of the crash course is to show you that there's a bit of a disconnect between an exponential money system that enforces a creed of constant growth and living on a spherical planet. In this section, a lot of you are going to find out that the planet is a whole lot smaller than you might have thought. Most of the reason is contained in this curve right here: population. Consider that the entire human population finally reached 3 billion people in 1960, and that projections call for adding another 3 billion people in only 42 more years. Before we contemplate 50% more humans in only 40 years, let me show you the pickle in which the current crop already finds itself. This year, there will be 70 million more humans on the surface of the planet than last year. 70 million. To put that in context, that is nearly 3 times as many people as live in the top 10 most populous U.S. cities combined. Worldwide population growth is equivalent to 3 of each of these cities each year for the next 40 years. More people means more demand for resources, more aluminum, more food, more consumer goods shipped to more places, and more cars. Always more cars. And in case anybody has the misperception that maybe this isn't such a big deal because maybe these people will be living in China in a dirt hovel with maybe a donkey in a wicker basket, let me show you one of the fastest growing cities in the world. In many respects, it is newer and more modern than most Western cities. This is what everybody aspires to. And people are the same the world over. We all want to live in bright, shiny cities, and we want to shop for nice things in nice districts. As a quick aside, China is said to have between 1.3 and 1.6 billion citizens. This means that the entire U.S. population of 300 million people, or 0.3 billion, would be referred to by the Chinese as a rounding error. In fact, if we combine the top 5 most populous cities in the U.S., we'd find that they would have fewer inhabitants than the largest city in China. But I want to return to the earlier statement that over the next 40 years, another 3 billion people will crowd onto the surface of the planet. One trait that humans share with all organisms is that we use the easiest to obtain and the highest quality resources first. When we use the Earth's resources, we start with the richest, deepest soils, with the largest trees, and the richest fishing waters. That is, we naturally exploit the highest quality resources first. At this point, I want to recall that oil is a finite natural resource, and because of this, we find that individual oil fields and collections of oil exhibit a classic extraction profile that resembles a bell curve. We can broaden this concept to create a generalized resource extraction profile, where we start with the closest, richest, and most accessible and highest grade resources first, before moving on to successively harder and poorer and thinner or more distant resources. What this means is that over time, the energy required to obtain those resources goes up, as do the costs. About this, there really can be no doubt. Here's an example. When we first came to this country, we were finding some pretty spectacular things just lying around, like this copper nugget. Soon, these were all gone, and we were onto smaller nuggets, and then onto copper ores that had some of the highest concentrations. Now we have things like the Bingham Canyon Mine in Utah. It is 2.5 miles across and 3/4 of a mile deep, and it started out as a mountain. It sports a final ore concentration of just 0.2%. Do you think we'd have gone to all this effort if there were still massive copper nuggets lying around in a stream bed? No way. Let's take a closer look. You see that truck way down there? It's fueled by petroleum, diesel specifically. If we couldn't spare the diesel to run that truck, what do you suppose we'd carry the ore out with? Donkeys? These trucks carry 255 tons per load. Supposing a donkey could carry 150 pounds, this means this truck carries the same in a single load as 3,400 donkeys. That's quite a lot of donkeys. My point here is that a hole in the ground a couple of miles across and 3/4 of a mile deep is a pretty spectacular display of the use of energy. When energy begins to get scarce, it seems unlikely to me that we'll be digging too many more holes like it, which means copper will become scarce. Now here's where the concept gets interesting. The amount of energy and money that is required to extract any mineral or metal is a function of the ore grade. We would measure that as the percent of the ore that consists of the desired substance. So a 10% copper ore, for example, would contain 10% copper, and 90% other stuff, like, I don't know, rocks or something. If we plot out how much other stuff we have to extract and then dispose of in pursuit of our desired substance, we get a chart that looks like this. Does this look familiar to you? It should. It's an exponential chart. It tells us that if we had an ore body with only 0.2% copper in it, we'd need to mine 500 pounds of ore in order to extract 1 pound of copper. I used this particular value because that happens to be the concentration of the Bingham Canyon mine. This helps to explain why this hole is so big. It tells us that without these giant trucks, we probably wouldn't be mining such low ore grades. It means that we are already on the far right edge of this bell curve in terms of energy and cost. Do we do this because we like the challenge of low ore grades? No, we do it because we've already high-graded all the other known ore bodies, and this is what we're down to. We do it because it's the best option left. We do it because in only 200 years, we've already burned through all of the better grades. Let's look at another example: coal. Coal production, as measured by tons mined, has been steadily growing at 2% a year since the 1940s. This sort of stable, continuous exponential growth is exactly what our economy and society demand. President Bush recently said that we have 250 years of coal left, implying that this red arrow can continue in this direction for another 250 years. In other words, there is no urgency here, just a whole lot of coal waiting for us to come and get it. But there's a wrinkle in this story. Coal comes in several different grades. The most desirable is shiny, hard, black anthracite coal. It yields the most heat when burned and has a low moisture content and is highly valued in the steelmaking industry. Then comes bituminous coal, offering slightly less energy per pound of weight, and then subbituminous, and then finally something called lignite, which is really, really low energy, high moisture stuff called brown coal that is pretty much only useful for burning. The next grade below lignite is rocks, which burn only slightly less vigorously than lignite. Let's look at the US history with mining anthracite. Notice a trend here? The reason we're not mining more of the stuff is because it's pretty much all gone. Our entire bequeathment of anthracite, formed over hundreds of millions of years, was largely used over a span of about 100 years. So we moved on to the next best stuff, bituminous coal. And here we might note that a peak in production was actually hit in 1990. Was this because we lost interest in this better grade of coal? No, it simply means that we started to run out of it. Naturally, we then moved on to the next grade, subbituminous coal, which we can see here making up the difference. And even lignite is getting into the game, although I don't expect to see this line really begin to move up until the subbituminous coal production has peaked out. Now we get to the really interesting part. Remember I said that the heat content or available free energy of coal got progressively worse with each grade? If we plot the total energy content of the coal mined instead of the tonnage, we get a very different picture. Where the tonnage has been moving up in a nice, steady, neat 2% climb, we note that the total energy has leveled off and has climbed by exactly 0% over the last 9 years. So we're using more energy and spending more money to mine more and more coal, but we're receiving less and less back from those efforts? Let's bring back this image again. Where do you think we are on this curve with respect to coal? Are the best years still in front of us? Do you feel secure with the 250 years of coal that the president has said we have left? The net energy of coal varies quite widely, but in extracting lignite, we are already pretty far down this net energy curve. Well, that's okay. We can switch to uranium, right? It turns out there's a little wrinkle in this story too.